happy Skeptics Day. Happy National Skeptics Day. Do you believe me when I say it's Skeptics Day? Good. If you don't believe me, then you're celebrating already. Okay, so if this is a fourth degree polynomial, we need to find at least two roots in order to get it down to a quadratic. Once we get it to a quadratic, we can solve it, quadratic formula, factor it, whatever. And we listed all the possible rational roots yesterday, and I'm not going to list those again because the video is already posted for 9A. But we did do the synthetic division process, 2, -7, -8, 14, and 8. And I think a boy offered up, I remember which boy it was. I won't name any names, but Zachary, do you remember what the two roots were? We tried -4 and 1. Both of those were on the candidates list, right? And we successfully determined that they did not work, okay? And then we took a random guess from a female. And Lauren, do you remember what that value was? 4, okay? And it turned out that it worked. So let's just kind of get back to where we were, because I don't know why it's not on here. Bring down the 2, and you multiply, you get 8, subtract 1, 4, -4, -16, 2, -8, 0. Okay, so that's where we were yesterday. What is the degree now of the polynomial whose coefficients are these, the depressed polynomial? It's degree 3. Now, we need one more root in order to determine what the quadratic is. Sometimes, though, if you write out your cubic, if you have 4 terms in your cubic, 2x cubed plus 1x squared minus 4x to the first plus 2, doesn't always work. But if you have 4 terms, there is a possibility that we could factor the cubic with 4 terms by what method? Grouping. Okay, so here's your option. You can either A, continue on by just randomly trying out values still from that original list on the cubic. B, you can write the cubic now as its own polynomial and then, bless you, redo the rational root theorem. Notice any values that are left at work that are roots are going to be now factors of 2 over factors of 2. So you can kind of make that candidate list smaller and then try again. Yes? It should be -2. I went too hasty and I made wasty. There we go. Thank you, thank you, thank you. There we go. So any values that work now are going to be factors of -2 over +2. So you can either do that, redo the list, or in this case, if we have 4 terms, you can attempt to factor by grouping. And factor by grouping, even if it has 4 terms, doesn't always work. Let's see if it works. Group those two together. And now because this next term is a negative, we have to be careful or careless when we group them? Careful. You need to do that and put a plus sign in between there. And on any quiz or free response, if you don't put the plus sign, even if you recover, you're going to lose a point. Now we pull out a common factor of x squared, and that gives us 2x plus 1. And now I factor out a -2, and it gives us 2x plus 1. And at this point, you know factor by grouping is going to work because you ended up with your 2x plus 1 right there. So if you then factored out your 2x plus 1, you're left with x squared minus 2, and that equals 0. So from there, you can now set each of those factors equal to 0 by the zero product property, and you can solve those individually. Now this one here, you could probably just look at it and say it's -1/2. This one here, if you separate, you get x squared equals 2, and what do you have to remember to not forget to do when you extract the square root? Plus or minus the square root of 2. So that gives me 1, 2, 3 more roots plus the 4 that we found by trial and error. I found 4 roots. How do I know when the search is over on this problem? When I find what? 4, right? Because what is 4 in the original problem? It's the degree. Good. And if it's a degree 4, we know it can have maximum 4 roots. And we found 4 distinct roots, which means they all must be multiplicity what? 1. So on the graph, it's going to what? Cross, bounce, or wiggle at each of those? Cross. Okay. So let's go ahead and answer the question. Haben Sie Fragen? No? Okay. Let's go ahead and write it out. The function's name is f. It asks us to find the zeros. So, comma, f of x, bless you, has roots of, or you could also say the roots of f of x are x equals 4, the one that we found by trial and error, negative 1/2, the one we found by factoring, and you can list these as plus, bless you, or minus, bless you, the square root of 2. Okay? Plus or minus the square root of 2. So that is specifically answering the question in a complete sentence, and you should get used to complete sentences. All right? And we're not going to graph it. We could, but we're not going to. Questions on that process? Okay, let's look a little bit more about these types of roots. Plus or minus the square root of 2. This is the first time we've seen roots like that. What kind of numbers are plus or minus the square root of 2? They are real numbers, but they belong to a smaller category of numbers called irrational. And it's the first time we've seen irrational, because up to now we've only seen rational roots, either integers or fractions, a ratio of 2 integers. Here, the first time we've seen rational roots. And notice they showed up as plus square root of 2 and minus square root of 2. If you actually write those values like this, 0 plus the square root of 2 and 0 minus the square root of 2, same thing, right? We just added a 0 in the front. Those numbers now appear to be what conjugates of each other? Conjugates of each other. And you know why they appear that way? Because they, in fact, are conjugates of each other. And so, this is going to lead us to the next theorem that we're going to be talking about, which we'll just scroll right down here and do it. It's called the radical conjugate theorem. And by radical, we mean irreducible radical, like square root of 2, square root of 5, square root of 3. Those are your irrational numbers. Square root of 4 is equal to 2. Okay, so it's not considered a radical. So the radical conjugate theorem says if you have a polynomial f of x with, now here's the kicker, it has to have rational coefficients. Remember, the rational root theorem only worked with a polynomial of integer coefficients. Here we're saying the radical conjugate theorem works if we have rational coefficients, which means they could still be integers, but now they could also be what? What's a rational number that's not an integer? A fraction, like 2/3, negative 1/2, okay? We cannot have irrational coefficients like square root of 2, square root of 5, or e or pi. Those would still be polynomials, but the radical conjugate theorem wouldn't apply. So if we have a polynomial with fractional or integer coefficients, then here's what the theorem says. If a plus the square root of b is a root, then guess what? X minus the square root of b is also a root. That's super important because you can't have one without the other. Irreducible radicals, roots, occur in pairs. They have to occur in conjugate pairs. What other graphical feature did we talk about that also had to occur in pairs? If you have one, you got to have another. I'll give you a hint. Local extrema. Local extrema. Local max or mins have to occur in pairs, right? Because if you turn around once, to keep the end behavior going the same way, you have to turn around again. So now we have another thing that happens in pairs. Irreducible radical roots have to occur in conjugate pairs, all right? And it's built into the quadratic formula, isn't it, Trevor? Look at your tattoo. In the numerator, it says what? Negative b, what comes next? Plus or minus. I know, you don't have to access the tattoo in class. I know it's kind of in that secret place. Yeah, it's built in, right? Negative b plus or minus. The conjugate radical theorem or the radical conjugate theorem is built into the quadratic formula. And the reason it's there is because, as we just saw, when you extract square roots, you have to extract both plus or minus. So that's why it's in existence. Okay? So, por ejemplo, if 5 minus 2 square root of 3 is a root, then guess what must also be a root also as well? 5 plus 2 square root of 3. So you could actually have a coefficient of your radical. Okay? Perfect. What if we have just x equals the square root of 7 plus 4 is a root? Then what also must be a root? What'd you say? Very good. You did not say the square root of 7 minus 4. Good, good. Can't get you on a Friday. It's negative square root of 7 plus 4 is also the root. In general, if you have two terms, the conjugate, it doesn't matter which one you change. You could always change the one in the middle in general. But this is not a general conjugate pair. This is the radical conjugate pair. So it has to be the radical term that gets the plus or minus, not just the second term, okay? And again, the radical is the one that gets extracted plus or minus. So if the radical happens to be listed first, make sure you're not changing the other sign. Good. What about if I just have x equals like the square root of 9? Is the negative square root of 9 also a root? Well, what's the square root of 9? 3. So that's another way to say 3 is a root. Does negative 3 have to be a root if 3 is a root? No. So it has to be an irrational, an irreducible radical. You can't have one without the other. And for right now, if we don't say the polynomial has rational coefficients, we're going to assume that it does, okay? We're going to assume that it does. I will try and mention it every time. So in other words, you can assume as for up to right now, through this section, the radical conjugate theorem applies. All right, let's try it out. Example 10, using synthetic division, find all the real roots of this fourth degree polynomial, given that the square root of 5 is a root. What's the degree of the polynomial? 4. If our goal is to get it down to a quadratic, I need to know how many roots. 2. They told me that the square root of 5 is a root. Can I assume that I have another root then tacitly or implicitly given? Yeah, what also must be a root? Negative square root of 5. Good, because look at your coefficients. 1, 3, negative 9, negative 15, 20. Are those all rational numbers? Yeah, they're all integers, so of course they're all rational. So the radical conjugate theorem applies. So if you'd like to, right here, go ahead and write it out. Negative 5, square root of 5 is a root, so also is negative square root of 5. So now do I have the two roots that I need to get down to a quadratic? Yes, 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 I do. Yes, good. So let's go ahead and write the coefficients in descending order. 1x to the fourth. FYI, if you ever are going to synthetically divide with radicals or later on imaginaries, you might want to leave a smidgen bit more space in between your numbers. Okay, just a little bit more than usual. So 1, 3, negative 9, negative 15, and 20. Just a little bit more space. You'll see why. Now, does it matter which root we use first, the negative or the positive square root of 5? Nah. So which one do y'all want to use? Positive square root of 5 is smart because negatives are, in general, a little bit trickier to deal with, and if you save the negative 1 per second, you're going to have one fewer term to synthetically divide with, right? So, makes sense. All right, so square root of 5 it is. Bring down the 1, and we prime the prompt. Now we multiply and we get the square root of 5. Now we add 3 plus the square root of 5. Is that the square root of 8? No, it's just 3 plus the square root of 5. So that's why you maybe wanted to leave a little bit more room, because now you have two terms down there. Now when you multiply, you have to distribute, don't you? You got to be careful. Square root of 5 times the quantity is the same as the square root of 5 times 3, which is 3 square root of 5, plus square root of 5 times square root of 5 is what? 5. So we end up with 3 square root of 5 plus 5. We're distributing down there. Now we add like terms vertically. So we get 3 square root of 5, and then we get like terms, negative 9 plus 5 is minus 4. Good. And we do it again. Square root of 5 times 3 square root of 5 is what? 15, because square root of 5 times square root of 5 is 5, times the 3 gives us 15. And then square root of 5 times negative 4 is negative 4 square root of 5. And now you add like terms vertically, and the quintes are gone. Minus 4 square root of 5. Now we are hoping that we get a negative 20 here in this last column. Let's make sure we do. Square root of 5 times square root of 5 is 5. And the 5 times the negative 4 does in fact give us negative 20. And we do end up with 0 right here. So that was some good intel that we came across right there. Square root of 5 was in fact a root of that polynomial. Now before we move on, let's look at this right here. What is the degree of the depressed polynomial? Third degree, right? If I had just started you off with that polynomial, 1x cubed plus 3 plus the square root of 5x squared plus 3 square root of 5 minus 4x minus 4 square root of 5. If I had handed you that polynomial all by itself, would the radical conjugate theorem apply to that polynomial? Are these rational coefficients? No. So the radical theorem would not apply, which now you can kind of appreciate, because what is the only irrational root of that polynomial? Negative square root of 5, right? That's the one we haven't used. So only negative square root of 5 is the root of that one, not the positive square root of 5. So you can kind of get a verification that the qualification of having rational coefficients makes sense. But anyway, let's go ahead and do the conjugate root next. Now later on, when we're synthetically dividing with 9th degree polynomials and 11th degree polynomials and some really, really fun ones, you're going to have a bunch of conjugate pairs that you're going to have to synthetically divide out. You want to get in the habit of always synthetically dividing your conjugate roots successfully one after another, okay? One after another, because if you do them one after another, you'll see what happens here, okay? Watch what happens when you do one after another. You bring down the 1, and you multiply, and you get negative square root of 5. Add like terms, what do you get in that column? 3. What happened to the radical terms? They canceled. Bye-bye. Multiply now, and you get negative 3 square root of 5. Add like terms, what do you get? Negative 4. What happened to the radical terms? They went away. See ya. Multiply, and you get positive 4 square root of 5. Add vertically, and you get 0. Notice that when you do the second iteration of your conjugate roots, your messy exponents will go away, and you're back down to now a happy polynomial with rational roots, or rational coefficients. So that's why you always want to do your conjugate roots back to back. You don't have to, but it's going to be a lot uglier if you don't. So just kind of a life hack, if you will. All right. Now, what's the degree of our depressed polynomial down here? 2. So that's what we want. So I'll write it out as 1x squared plus 3x minus 4. I will set it equal to 0. And now, please, oh, please, please let it factor so I don't have to show off with the quadratic formula. I don't like to boast or brag. Let's see, that's an x, that's an x. It looks like it should be a plus 4 and a minus 1. It's going to work. So from that, we're going to get the final two roots of negative 4 and 1. So I got 2 roots from there. I got my 2 conjugate roots up there. That's 4 roots. Are we done with the search? Yep, because it was a 4th degree polynomial. Now it said to find all real roots, so let's go ahead and give a summative statement. What's the name of our function? G. So, and you can do it like this now, the roots of g of x are x equals plus or minus the square root of 5. You still want to list the ones that were given. In this case, they gave us the square root of 5. You still want to list it. It's still a root. But then all of the ones then that you found in addition to those, comma negative 4, comma 1. So get in the habit of writing your summative statement in a complete sentence. Now let's see if we can go ahead and write g of x in factored form. The leading coefficient is 1. That's nice. So that's my a value. So g of x could be written as, well, let's see. If positive square root of 5 is a root, what's the associated factor? X minus the square root of 5, right? And if negative square root of 5 is a root, what's the associated factor? X plus the square root of 5. If negative 4 is a root, the associated factor is x plus 4 and then x minus 1. This would be considered both prime factorization because those are all linear factors, and it's also considered the factor theorem version because it's all 1x, 1x, 1x. So this is a pretty nice version. You could just pluck the roots right off of there. But notice that these 2 factors in the front, they just kind of look ugly, okay? Relatively ugly because you have the radicals there. So there's going to be another version of the factored form that I call reduced factored form. And reduced factored form basically means this. If you ever have any factors with radicals or later on imaginary roots in them, you want to expand those conjugate factors before you walk away, just to make it look prettier. Okay, you don't have to expand the whole thing out, just expand your two conjugate factors. So let's go ahead and do that. G of x would equal, now the product of two conjugates, remember, is a difference of squares, and it doesn't have to be perfect squares. So we get an x squared on the front, the inner and outers cancel, right? Minus root x plus root x, they're gone, and we're left with minus square root of 5 times square root of 5, which is minus 5 times the other two, and that's where you would stop. Now, this is not a prime quadratic factor. X squared minus 5 is not prime because it does factor into the product of two linear factors, but I'm going to call that reduced factored form. We got rid of the radicals, and later on we're going to get rid of the i's. It just looks prettier. So if we had to plug in a number and evaluate it, we could plug into this and evaluate it a lot easier than working with radicals and later on imaginaries, okay? So let's jump down here and just state that. A function is said to be in reduced factored form if basically it's in linear factors except for the ones that have radicals or imaginaries or irreducible quadratics, like x squared plus 5. That'd be an irreducible quadratic. And you'll see later on that that's going to come from imaginary solutions. So on example 11, let's go ahead and write a polynomial whose name is f in lowest degree, whose properties are this, all right? So let's see. We're going to assume that the radical conjugate theorem works. We're going to have integer or rational coefficients. So f of -1 is 0, which means -1 is a what of f? A root, okay? Negative square root of 2, f of that equals 0, so negative square root of 2 is also a root, which means guess what else is also a root? Positive square root of 2. So f of positive square root of 2 also equals 0. The next one says 2 plus the square root of 3 is a root. So guess what else has to also be a root also? 2 minus the square root of 3 is also a root. So they gave me 3 roots, but from the conjugate radical theorem, I can assume 2 more. So if I want to write a polynomial of lowest degree, I'm going to make all of those multiplicities a 1, okay? Otherwise, I'd have the option of wiggling or bouncing there and adding some extra roots just because I want to. So at the least, we have 1, 2, 3, 4, 5 roots. So guess what the degree is going to be? 1, 2, 3, 4, 5. If I have at most 5 roots, it's got to be a 5th degree. 5th, right? The number of roots is always the degree. The relative extrema, remember, is always one smaller. And then they occur in pairs. All right, now here's another point that they gave me. F of 0 equals 5. Is that an x-intercept? That happens to be a y-intercept, but more importantly, it's just another point not on the x-axis. So we've done that before, too. That's going to allow us to stretch it or compress it or reflect it to make sure it passes through a point. That's going to help us find our value of A. All right, so step 1, let's go ahead and write the general equation. We'll write the general equation. That means that we're going to have our A in the front, A. Now let's just go ahead and start listing factors. If -1 is the root, what's the factor? X plus 1. If negative square root of 2 is the root, what's the factor? X plus the square root of 2. Conjugate factor next. If positive square root of 2 is the root, then x minus positive square root of 2 is the associated factor. Now here's where you got to be careful. If 2 plus the square root of 3 is the root, what is the factor? No, not 2 minus, that's the other root. We have 2 terms in our root, but remember, to get the factor, it's always x minus the root. For some reason, students, when you have a 2-term root, they want to just forget about the x. If A is a root, x minus A is a factor. So if 2 plus the square root of 3 is a root, x minus the quantity 2 plus the square root of 3 is the factor. Okay? And notice, because it's 2 terms and I'm subtracting, what did I put there? Mis amigos, my friends, parentheses. And then if 2 minus the square root of 3 is a root, then x minus the quantity 2 minus the square root of 3 is also a factor. Okay, So that right there, believe it or not, is in the factor theorem factored form, because it's just x minus, x minus, x minus, x minus. But it's not in reduced factored form. I've got radical conjugate factors twice. So what you want to do is expand those out. Now, do you think we want to expand those two together, the ones that I just highlighted? No. Only expand out the conjugate pairs. So do those and those. All right, so f of x equals a. Oh, and by the way, you want to do this before you find a, because it's going to be a lot easier to find a. Now these, of course, just like we saw, those are conjugates. You're just going to get x squared, middle terms cancel, and you get minus 2, x squared minus 2. But notice on the other ones, the fact that the root has 2 terms and you're subtracting, it's going to be a little bit harder if you just do it by difference of squares. So let's go ahead and do an extra step in between. Let's distribute the negative. X minus 2 minus the square root of 3, and x minus 2 plus the square root of 3. And now on the next line, I'm ready to expand those. I can't use FOIL anymore, though. Just like when I'm using a microwave, don't use FOIL. In this case, FOIL only works with 2 binomials. We have 2 trinomials. So instead, we'll just distribute. We'll just distribute. So what I'll do is I'll take my first one, x, and I'll distribute it through to the next 3. So I get x squared minus 2x plus the square root of 3x. And notice that x is outside the radical. And then I'll move over to the next one, negative 2. So I distribute it through and I get negative 2x plus 4 minus 2 square root of 3. And then I move over to the final one, negative square root of 3 distributed is negative square root of 3x on the outside plus 2 square root of 3. And then finally minus square root of 3 times square root of 3 is 3. Now that looks like one behemoth of a factor. But just like when we had my favorite problem with the x plus h, you will know if you expanded it correctly, because just like in this other conjugate factor with the radicals went away. Same thing should happen here. All right, so let's just rewrite everything else down. F of x equals a times x plus 1 times x squared minus 2. And let's see what happens with your radicals. They should cancel, so make sure that they do. I have a positive square root of 3 times x and a negative square root of 3 times x. Those cancel. I have a negative 2 square root of 3 and a positive 2 square root of 3. So they do, in fact, cancel. If they don't just keep moving on. Go back up and figure out why. Now we just collect all the like terms. We have a 1x squared, but I have 2 linear terms. I have a minus 2x minus another 2x. That's minus a 4x. And then I have 2 constants. A plus 4 and a minus 3 makes it a plus 1. And notice that that cleans up very, very nicely. So this would be your general form in reduced factored form. Now, if you had to find the roots of x squared minus 4x plus 1, you probably wouldn't be able to factor it into x plus or minus, or x minus 2 plus or minus square root of 3. You'd have to use the quadratic formula, in which case those 2 roots would emerge. But now we can find a very easily. So now we're going to plug in the 0.05. So here's what you want to do. Always getting in the habit of signaling your intention. We're going to say at 0, comma, bless you, 5, colon, at 0, 5. You know what that tells me? That tells me, hey, I was about to plug in a 0 for x and a 5 for f of x. And I'm like, cool. I know what you're doing now. So we get 5 equals a. 0 plus 1 is 1. 0 squared minus 2 is negative 2. And 0 minus 0 plus 1 is 1. Look how easy it is to plug in a 0 for x once we have it in reduced factored form. We don't have to worry about the radicals anymore. They're gone. So now if you solve, you get a equals negative 5 halves. Are we done once we find a? No, now we plug it back in, so we make that summative statement, and a great transitional word to the end is so, comma. You plug it right back in up here to the one that I asterisked. That's the general form in reduced factored form. So f of x equals negative 5 halves times x plus 1 times x squared minus 2 times x squared minus 4x plus 1. And that is about as pretty as it's going to get without expanding it completely out. Reduced factored form with our value of a there. So again, notice that's not prime factored, but it is reduced factored form. No ugly radicals, and later on, no ugly imaginaries. Okay, you got the idea? Very, very carefully. Let's just quickly recap. We used the radical conjugate theorem because we had two radical roots, so I know that their conjugates were also roots, so we changed the sign of the radical. Then I came through and did f of x equals a, and then carefully x minus each root, x minus, x minus, x minus, x minus, putting parentheses around the binomial roots. Then I expanded the two conjugate pairs, both of them, got it, combined like terms, got it in reduced factored form. Then I plugged in the point not on the x-axis that was given, found a, and then finally I rewrote it by plugging it back into my reduced factored general form. And then I smiled. We always smile at the end, right? If we're not smiling all the way through, and some of us are, right, we at least smile at the end. Not because we're done with the problem, but because there's more math to be had, right? That looks like a very sincere smile. I'm like, that's what it looked like. Yeah, I like it. I like that we could joke about not smiling for real. Okay, example 12, very quickly, example 12 is like the warm-up. Like the warm-up, it's going to be the specific division algorithm that we talked about yesterday and we warmed up with. So see if you can do this one very quickly. We're on pep rally schedule, so we get out of here at 10:25. We have about 5 minutes left. Not much time. We should probably do it together then. I have a 1,000th degree polynomial. I don't want to know what the quotient is when I divide by x plus 1. I just want to know what the remainder is. Do we need to do long division or, heavens forbid, synthetic division and write down all those zeros that we're missing from the other terms? No, because I know that the remainder, when I divide this by x plus 1, is nothing going to be nothing more, than this 1,000th degree polynomial evaluated at what value of x? -1, the root of that factor. Now, instead of calling it f of x and saying f of -1, here's another way you could do it. You could just say at x equals -1. And then you plug it in. Anything that's an even degree, remember, is going to stay the same sign. Anything that's an odd degree will change sign. So we're going to get a 6 minus 17 becomes minus 12 plus 26. And if you simplify that, you're going to get 3. So, can anyone give me an ordered pair that lives on the graph of that 1,000th degree polynomial other than the y-intercept at 0, 26? Can anyone else give me another ordered pair that lives on the graph? No, because when I plug in my -1 here and raise it to the 562th power, so it's negative. That one stays the same. So I get 3. So what's another ordered pair on the graph? -1 comma 3. Very good. That's an ordered pair on the graph. But remember, 3 is also now the remainder when I divide that by x plus 1. So is x plus 1 a factor of that? No, because 3 is not what? 0. So remember on the quiz, if you had to justify, you wouldn't say that x plus 1 is not a factor of that because the function value there is 3. You would say it's not because the function value is 3, and 3 ain't 0, right? We're looking for zeros. All right, the last type of question we have, we're going to skip this. This is the division algorithm. And Trevor, that's what you were asking me about on the worksheet. Okay, we're going to skip that and come back to it. I think that's worksheet problem number 6, so you don't have to do that one. But we are going to do the last one, number 15, because it ties right into that division algorithm. If x plus 2 now is a factor of this cubic polynomial, what's the value of k that'll make it sure that it is? Well, if we want x plus 2 to be a factor, then by the division algorithm, when I plug in a -2, what should be the remainder? 0. So this one you could do like we just did by direct substitution. You could just say at x equals -2, you're going to get 3 times -2 cubed is -8, plus k times -2 squared is 4, minus 2 minus the other 2, and of course now we force it to equal 0. we force the function value to be 0, so it's an x-intercept. And if you simplify, you get negative 24 plus 4k minus 4 equals 0. So negative 28 plus 4k equals 0. So 4k equals 28. And if you divide through, you get k equals 7. So there you go. That forces then x plus 1 to be, or x plus 2, sorry, to be a factor because it forces negative 2 to be a root. Got it? Now this one you could also do synthetically because 3 is a pretty small manageable exponent rather than 1,000. If this was with to the 1,000th degree, this is how you would do it. But here's what it would look like synthetically. Just some of y'all like to see another method. But notice that the direct sub worked pretty well there. So you don't have to do it this way. You would write out the coefficients 3k, 1, negative 2. And now we would synthetically substitute a negative 2. And we bring down the 3 and we get negative 6. So here we get k minus 6. If you distribute like we did with the radicals, you would get negative 2k plus 12. Adding, you get negative 2k plus 13. Distributing now, you get 4k minus 26. Adding, you get 4k minus 28. And of course, that's your remainder box. And what do we need to force the remainder to be now? 0. So you end up with a linear equation in the remainder box. And of course, that turns out to be the exact same equation we eventually solved over there. So either way, I don't care, you get the right answer. You'll probably have a multiple choice question like this. All right, so that takes care of the notes. We finished. We did it. Worksheets due on Monday, minus the problems that say to write it as the product of the quotient times the divisor plus the remainder. Forget all that. I think it's just number 6. We'll have a group quiz on Monday. We'll talk about the test, and then we'll test on Tuesday. So have a